If you've ever stopped to look at a speaker while it's playing music, it's actually an incredibly simple machine that really only does two things. It pushes out air and pulls in air. Because of that simplicity, turning math into music is not that hard. All we need is a precise map of where the speaker should be at every split second. So we're going to make that map from the most basic building block in math, the function. A function is just a rule or recipe, a little machine where you put a number in and get another number out. In this case, the number going in is time, how many seconds have passed since the song started, and the number coming out is position, where the speaker cone should be. We're going to write a math equation that acts like a motion guide for the speaker, telling it exactly how far to move in or out at each moment, from -1 to +1. When the speaker follows those instructions, math turns directly into sound. To create this movement, we need our first ingredient, vibration, because vibration is sound. In the world of math, the smoothest and most perfect way to move back and forth is called a sine wave. If you graph it, it looks like this. Now, if you play a single sine wave, it won't sound like a violin or a trumpet. It creates an electronic beep sound. Real instruments sound rich and complex because they vibrate at many frequencies at once, called harmonics. But for today, we are sticking to the basics. When we play a sine wave, we get something like this. The next thing we need to do is to control how fast the vibration of our speaker happens, which brings us to frequency. As you've heard, a sine wave is just a low, inaudible hum. But to make music out of it, we need notes. In math, notes are just numbers that describe how many times the sine wave wiggles back and forth in a single second. If you tell the wave to vibrate 261 times per second, your ear hears middle C. Speed it up to 440 times per second and you hear the note A. By simply changing this one number in our equation, multiplying time by a specific value, we force the sine wave to wobble at exactly the right speed, letting us tune our math to any pitch on a piano. However, if you actually played that equation as is, it would sound terrible too. That's because pure math waves never stop. They're either fully on or fully off, screaming the same note forever at full volume. Real instruments don't behave like that. When you strike a piano key or pluck a guitar string, the sound bursts out loudly and then immediately begins to fade into silence. To make our math sound musical, we have to simulate that natural fade using an envelope. A sound envelope describes how a sound's volume changes over time. Instead of staying loud forever, real sounds start strong, fade away, or sometimes grow and hold before ending. An envelope acts like an automatic continuous volume adjuster, shaping a sound from the moment it begins to when it disappears. By controlling how quickly a sound rises, sustains, and fades, the envelope is what makes a note feel sharp like a pluck, soft like a pad, or short and percussive like a bell. In math, this is often built using the number e with a negative exponent, the same number that describes natural decay, like a hot cup of coffee cooling or a bouncing ball losing energy. This creates a smooth curve that slides from loud to silent, like a playground slide. When we multiply our buzzing sine wave by this fading curve, the sound starts strong and quickly tapers off, transforming the robot-like beep into a pleasant bell or piano-like ding. But for this melody, instead of a normal exponential decay, we are going to use a Gaussian or bell curve. This uses the number e raised to a negative squared power. Unlike a simple fade out, a bell curve starts silent, quickly swells up to a peak, and then smoothly fades out. This gives our instrument a softer, rounder feel, almost like a glass harmonica or a soft mallet strike. Now that we have a single beautiful note, the final step is turning it into a melody and actually getting it out of the speaker. We do this by copying that note, shifting each copy in time and choosing when it should start, because we don't want all the notes playing at once. In math, that's as simple as telling the equation, don't begin until time equals 1, or 2, or whatever moment we want. For every note in the song, we pick a pitch, pick a start time, shape the fade, and then finish the song by literally adding them together. Note 1 plus note 2 plus note 3. So the computer pushes the speaker according to the sum of all those waves. Finally, the amplitude or volume. In our graph, amplitude is simply the height of the wave. By default, our sine waves swing from -1 to +1, which represents 100% volume in the digital world. Since we are playing a melody where the notes are spaced out rather than slamming down as a giant chord, the waves don't pile up on top of each other too much. This means we can safely leave the amplitude at the default 1 without the sound cracking or distorting. Now let's make a simple short melody using what we just learned above. But before that, here's a table of musical notes and their corresponding frequencies. These are the notes of our song. Each term in the function represents one note. The numbers inside the parentheses, like 0.1, 0.35, or 0.6, shift each note forward in time, which is how rhythm is created. The constant -200 controls how tightly each note is packed in time. Larger values make notes shorter and more percussive. Smaller values let them ring longer. Finally, the reason we use 2π is because sine waves naturally repeat every 2π radians. Using 2π ensures the frequency we choose corresponds exactly to cycles per second, so the pitch we hear matches the musical note we intended. And by adding everything together, we get... We've built a short melody, but to make it sound like a piano, we'd need to add dozens of smaller sine waves on top of each note. But the math principle is exactly the same. If you want to see the full corrected version, subscribe and tell me in the comments.